In this segment, I want to start talking about waves. Well, what are waves? You've all seen an ocean wave. And so you can picture what a wave looks like on water, and sure, that's a kind of wave that we're going to talk about here. But you're hearing me right now because I'm producing sound waves, which are recorded on my computer and reproduced on yours. But one way or the other, you're hearing a sound wave right now. It turns out you're looking at a light wave. As we'll talk about in the next chapter, we can understand a lot of the chemistry you may have learned in terms of electron matter waves. So a wave model can help us understand a wide range of very interesting phenomena. First, we need to distinguish between mechanical waves and non-mechanical waves. Mechanical waves involve the motion of a substance, and that substance is the medium. One of the easiest ways for me to demonstrate to you is what we call a wave on a string. And it's easier demonstrated with a spring, but with a string it works very similarly. It just moves a little faster and it's harder to show. So here I have this plastic spring with a very low spring constant, and I can show you a wave. Here's a wave. Great, there we go. That was a wave on a spring. So does this wave require a medium? You bet. The wave does not exist if there's not the spring to carry it. Because a sound wave requires something to move through. We're used to having sound waves move through air. That's how you and I experience sound waves most of the time. But if you were a dolphin, you'd experience sound waves moving through water. However, if the moon blew up, we would see it, but we would not hear it. Why? Because there's no air in space to carry that sound wave. So sound waves require a medium. Usually that medium is the air. But if you've ever lived in an apartment and could hear your neighbors, then you know that sound can travel through a solid as well. If you drop a pebble into the water, then you'll see those waves expand out. Those waves expanding out are water waves, and somewhat obviously, a water wave cannot exist without water. So those are all examples of mechanical waves. We'll talk about some non-mechanical waves in just a second. For right now, let's talk about the wave speed. The wave speed is the speed at which the wave disturbance travels. So you toss that pebble into the pond, you see those ripples traveling out. If you were to time how far each of those ripples went, in how long, then you could calculate the wave speed. It's how fast one of those ripples is moving. For a sound wave, a typical speed is 343 meters per second. That's something like 1,100 feet per second, something like 750 miles per hour. That's a typical speed for a sound wave. As we'll talk about in a future segment, the speed of a sound wave is not constant, but rather varies somewhat. However, for the sake of this class, if you are asked to do something using the speed of sound, and I haven't told you specifically to use something different, use 343 meters per second. As I already mentioned, the speed that a ripple moves on water, that is the wave speed for a water wave. Light is a wave, and light travels very fast, but not infinitely fast. That's something that scientists didn't know about until right around the turn of the century, between the 1800s and the 1900s. The speed of light is 300 million meters per second. That's very fast. About 186,000 miles per second. Very fast, but not infinitely fast. That is the wave speed. What are non-mechanical waves? Well, non-mechanical waves do not require a medium to travel, which is sort of weird, right? If you're thinking about a water wave, or you're thinking about this wave on the string that I just demonstrated, then it seems like maybe a wave should require a medium. And indeed, this was a subject of great debate up until about 1900. Around 1900, scientists started to realize that electromagnetic waves, which are also known as light, can travel through empty space. Whoa. Well, what is an electromagnetic wave? Well, so in an electromagnetic wave, which we know as light, although it can take on different forms, radio waves are also electromagnetic waves. In an electromagnetic wave, what is it that's actually wiggling? Well, it's electric and magnetic fields, whatever those are. We're going to learn a lot more about that here in a few chapters. But you've actually probably had some experience with electric and magnetic fields. Here I have a magnet, and here I have a piece of metal. If I bring the magnet next to the piece of metal, what will happen? the metal jumped up and touched the magnet. Notice they didn't even have to be touching for that to happen. Somehow, the piece of metal knew that the magnet was there. How did that happen? Well, we can think of it as the space around the magnet is permeated with a magnetic field. When that magnetic field interacts with the metal, it responds. So that's a magnetic field. You've also probably, though you may not realize it, had experience with electric fields too. If I pull off a couple of pieces of Scotch tape here, it turns out they will be electrically charged. And if I bring them close to each other, they repel each other. Look at that. And it's not just the curvature of the tape, right? If I bring them together like this, we'll see that they also repel each other. Oh, they're attracted to me, but they repel each other, right? That's pretty interesting, right? This is attracted to me and not the sticky side. This is the sticky side over here. Yes, it sticks to me. That's not surprising. But notice this, it gets attracted to me on this side. That's not the sticky side. Why? An electric field. Okay, a lot more on that in a future chapter. But for right now, let's just leave it at that. What's wiggling is an electric and magnetic field. It's not a thing. It's not a physical thing you can hold in your hand. So electromagnetic waves are not mechanical waves. And there was a big debate. In fact, scientists had proposed that maybe space is filled with some ether, right? We knew that electromagnetic waves can travel from the sun to the earth. And so all of the waves that we interact with here on Earth, except for light, basically, are all mechanical waves. And so scientists were really used to dealing with sound waves and waves on a string and water waves. All of these things require a medium. So if light's a wave, how can it propagate through space if there's no medium? Scientists said, well, it's because space is filled with this thing, I don't know, let's call it the ether. We've learned that we don't need the ether. We've learned that electromagnetic waves, they just propagate through empty space. They are just non-mechanical waves. We will learn in future segments that we can actually understand the structure of an atom much better by understanding electrons not as tiny little balls orbiting a nucleus, but rather as matter waves that are around the nucleus. It's so weird to think about. But it's really a very useful model of the atom. Super weird. We're going to talk a little bit more about that as we go on. Okay, so what is a wave? You know, if I think about this wave on a string, again, this is possibly the easiest way for me to demonstrate. If I just give a little pulse here, right, then we see it travel down and back, don't we? And it's happening pretty quick, but we can see that happening. Right? And I think most of us get a sense that something travels down and back. What? Well, the spring didn't go anywhere. The spring is still here in my hand. So it wasn't the spring that went down. None of these little coils actually changed places, right? So it's not the spring itself that went somewhere. What was traveling? We had a sense that something went down and back. Well, we would say the disturbance traveled down and back. We could maybe be a little bit more precise, and we could just say that was some energy. So what is a wave? It's energy in motion. As I'm speaking into the microphone in my computer, sound waves are traveling from me to the computer. But air isn't, right? I'm not blowing into the computer. If you were here in this room, it's not me blowing air into your ear. No, what's traveling from me to the microphone on my computer is energy. It is the energy that travels from me to the microphone. So for mechanical waves, the energy is going somewhere, and the medium itself just vibrates back and forth. So again, with the example of the sound wave, energy flows from me to the microphone in my computer. As it does so, the air in between me and my computer vibrates back and forth like this. It doesn't go anywhere, right? If there was a breeze in the room, that would be the air going somewhere. I'm not creating a breeze, right? It's just vibrating. So energy goes somewhere, the air vibrates, but doesn't go anywhere. For a non-mechanical wave, there's literally nothing moving. There's no thing moving. It is pure energy in motion. It's sort of crazy to think about, but it's a really cool idea. We can do some further categorization of waves. We can categorize them as either transverse or longitudinal. A transverse wave is what I've modeled here with the wave on the spring. And this happens pretty quickly, doesn't it? Right? And so it's maybe hard to kind of wrap your brain around exactly where that's going. But if we look at this picture, we can see, if we were to take a quick picture of this, we'd see that this disturbance travels along the string. Right? Notice that as this disturbance travels along the string, the wave is moving in this direction, and the medium is moving in this direction. If we were to think about one little coil of this spring, we would see it moving up and down as the disturbance went past. The wave moves here, the medium moves here. Notice that motion is perpendicular. For a longitudinal wave, the wave moves in this direction, and the medium moves parallel to it in the same direction. I have a real quick simulation that I'd like to show you that helps to demonstrate this a little bit slower than the wave on the string. Here we see a simulation of a transverse wave. Notice that the wave itself, the disturbance, is moving to the right. Each individual part of the wave moves up and down as that happens. Now, I got to be clear here. What's important is not up and down and to the right. What is important is that those two motions are perpendicular to each other, right? If I was to turn my computer screen sideways, or you could lay on your side, then you would see the wave moving up and the individual particles moving side to side. So the important thing here is the relationship between the direction that the disturbance or the energy is traveling in and the direction that the medium is vibrating. They are perpendicular in a transverse wave. Here we see a simulation of a longitudinal wave. Notice we all get the sense that something is moving from left to right. But what is it? It's just the disturbance. Notice that as the wave moves to the right, we see each individual particle of the medium move back and forth. In this case, the motion of the medium is parallel to the motion of the wave. And again, it's not left and right that matters here. It's the relationship. A longitudinal wave could be moving in this direction, in which case the particles that make up the medium that the wave is traveling through would be moving like this, right? So what's important is the relationship. In a longitudinal wave, the motion of the medium is parallel to the motion of the wave. In a transverse wave, the motion of the medium is perpendicular to the motion of the wave itself or the disturbance. Okay, so now we've seen what a transverse wave is and what a longitudinal wave is. This is often demonstrated with a slinky. It's hard to do in my basement, and so I've shown you that simulation instead. The people wave in a stadium is a transverse wave. Here we get the sense that there's something moving to the right. What is it? Nothing. It's just a disturbance, right? We get this sense that something's moving to the right. The individual medium moves up and down. The stadium wave is a transverse wave. Here's a simulation of a sound wave. And a sound wave is a longitudinal wave. It's the longitudinal wave that we will talk about the very most. Notice that we all get the sense that there is a disturbance moving to the right. But what's moving to the right? None of those individual dots are moving to the right. Look at one of them and see what it does. Oh, I don't know. How about this one? Let's look at what this dot does as the wave moves past. It moves side to side. This is a very good demonstration of what's happening in the air between me and the microphone as I'm speaking. The sound wave moves from my mouth to the microphone. As it does so, the individual particles that make up the air, in this case mostly nitrogen molecules, are moving back and forth like this in order to transmit that sound wave. Examples of transverse waves include a water wave, a wave on a string or the spring as I've demonstrated, the wave at the stadium. If you've had some geology, S waves in an earthquake are transverse. Examples of longitudinal waves are sound. Sound is the longitudinal wave that we're going to talk about the most. The slinky waves, and again, if you've had some geology, P waves in an earthquake are longitudinal waves.